Okay. Find the derivative of y equals negative 15. 1 times negative 15 is 15, and then x to the 1 minus 1 becomes x to the 0, so the x disappears. So y prime, or dy dx, whichever notation you like, negative 15. H of u is 3u squared minus 8. H prime of u can be written as dh of u, or just dh over du. And it would be 3 times, bring the exponent down, 2, u to the 2 minus 1. And then negative 8 actually disappears. Ah, thank you. Good. So what you have left is 3 times 2 is 6, u to the first power minus 0, and I don't usually write the 0, so I just put 6u. You have to rewrite p of t to be 10.43 t to the negative 1 power. Then bring your negative 1 power down in front, times what you had to start with, but reduce the power by 1. So p prime is dp over dt, or negative 10.43 times t to the negative 2. You have to rewrite square root of x as x squared. So then f prime of x is df over dx, and it is written as negative 2 comes down in front, so negative 2 times 2.4 is negative 4.8, and then negative 2 minus 1 makes x to the negative 3, and since x is to the 1/2 power, the 1/2 comes down in front, and reduce the 1/2 by 1, and it becomes negative 1/2. Now if you wanted to shift those around and put them back in radicals, you could. I did not. They're perfectly correct without going back to the radicals, but you can. And you can also move things to the denominator. I know what all the equivalent forms are, but I go to the first one I get, and when I get the derivative done, I don't always simplify it. And my math lab will not force you to simplify your derivatives. It'll give you credit as long as the equivalent expression is correct. Scoot up a little bit. So we have y equals 1 plus x squared minus 3 over x. Once again, the x has to have a negative 1 power to be able to use your power rule. So the derivative of 1 is 0. The derivative of a constant is always 0. Plus 2 times x to the 2 minus 1, bring the square down in front, minus the negative 1 power times 3x to the, now it's going to be negative 2 power. And since the 0 disappears, we have 2 times just x plus 3x to the negative 2. And then for q of w equals negative 2.3w, the derivative q prime, or dq over dw, is just negative 2.3. Because there again, you bring the power of 1 down, doesn't change anything, but when you reduce the exponent by 1, w to the 0 power becomes 1. Number 7, we had square root of x, which there again is going to have to be x to the 1/2, minus 5.09x, 1/2 x to the 1/2 minus 1, minus 5.09, the x disappears. So we have 1/2 times x to the negative 1/2 minus 5.09. And g of t was the easiest one on there. The derivative of a constant is always 0. Number 9, L of t equals 0.22 t to the negative 6.3 power. So L prime, or dL dt, is negative 6.3, bring the power down in front, times 0.22 t, and then reduce the power by 1. So you have 13, and I messed up. This needs to be negative 13. Forgot my negative sign. Negative 0.1386 t to the negative 7.3 power. And then our last one, 4 brought down in front of with the negative 6 gives us negative 24. 4 minus 1 gives us x to the 3rd. 2 down with the 5 brings that to a 10, and x to the 2 minus 1 is just x, and the understood coefficient of x there is just 1, and the x drops out. I hope you did well. If you didn't, you're going to have another chance on Tuesday. Because I'll have one of these seriously every day for a while until almost everybody's making 9s and 10s on it.
Number 9, will it hurt to say that your exponent of negative 713 cannot be negative? Will it make you?
No, not for what I do. So now we will begin, and I don't remember if I think I stopped here because I didn't want to have to tell you how to do that problem. At least not at that point. So now we're going to talk about the sum and difference rule. And actually we used it on that last handout a little bit because I think I did explain to you that you just take the derivative of every term. So actually doing these is relatively easy because all of these were similar to what's on the quiz, but 3 and 4 aren't. So I'll do examples 1 and 2, just as a way of refreshing you, and then we'll talk about 3 and 4. Then I'll come back to this. What that sum and difference rule says is that if you have a function and you need to take its derivative, you basically look at each term individually and take the derivatives. So we're going to have the derivative of this plus the derivative of that will give us f prime of x, or df dx, whichever way you want to write your notation. This one's simply going to be 3 times 6x to the 3 minus 1. And this one's going to be 2 times 15x to the 2 minus 1. So f prime of x, or df dx, is equal to 3 sixes is 18, x to the 3 minus 1 is 2, plus 2 times 15 is 30, x, and 2 minus 1 is 1, so you can write the 1 or you can leave it out. Very similar to what we just did on the quiz. P of t is the same exact thing, except we've got 3 terms, and one of them is a subtraction, one of them is an addition. So again, we differentiate term by term. So P prime of t, or dp dt, 4 times 12 is 48, t, 4 minus 1 is 3, minus, this has to be changed to t to the 1/2 power. So 1/2 times 6 is 3, and t to the 1/2 minus 1 is negative 1/2. And this has to be changed to 5t to the negative 1. So plus negative 1 times 5 is negative 5t to the negative 2, with or without the parentheses. You can drop the parentheses and just put that as minus 5t to the negative 2. Now, it is not wrong, but it is also not necessary to go this step. 48t to the 3rd minus 3 over the square root of t, because that's what t to the negative 1/2 is, minus 5 over t squared. That's an equivalent form. It looks nicer, it looks cleaner than the other one does, but it isn't any more or any less correct. It's the same thing. So if you can't go to this form, that's fine. You need to be able to at least get this part. Are we okay so far? Okay. The algebra really comes in more with problems like this, because you're going to have to write that in an equivalent form before you can do anything with it. And you're looking at it thinking, how am I supposed to do anything with this? Well, you got to remember, number one, that both of these terms are being divided by x. So it might look like it's an easier thing to take a derivative of if we first put x cubed over x plus 3x to the 1/2 over x. And then hopefully you know that x cubed over x reduces to x squared. And 3, we've got x to the 2/2 in the bottom and 1/2 in the top. So we're going to have x to the 1/2 minus 2/2 is x to the negative 1/2. You subtract your exponents. That's why that's negative 1/2. So now we've got something we can use the power rule on. And we can find g prime by saying that g prime of x equals 2x to the first power. Negative 1/2 times 3 is negative 3/2 x, and subtract 1 from 1/2, you get negative 3/2. Use your calculator on the fractions if you need to. So there's your derivative. Now, it is perfectly fine and it is equivalent if you go ahead and write it this way, but you don't have to. Minus 3 over 2, and this brings the x to the denominator. And the square tells you it was square rooted, but the 3 in the numerator tells you it was the square root of x cubed. And you could even simplify that further, so be glad I'm not picky about algebra, by changing it to 3 over 2x square root of x. But I think this is just fine. And I want to see that step regardless of whether you do the other two or not, because I want to know if you made a mistake, did you make a mistake in the calculus or did you make a mistake in the algebra? I'm a lot more forgiving of algebra mistakes than I am calculus mistakes, because that's what I'm teaching now. I'm not teaching you algebra. Okay? This one, you look at it and you think, there's no way I can do that. I don't have anything that had parentheses in it. But what does this actually mean? That's right. It actually means take what's in the parentheses and multiply it by itself. So if you've forgotten how to multiply your polynomials, you might have to review a little bit. So 4x times 4x is 16x to the 4th. Minus 3 times 4 is minus 12x to the 3rd. Minus 3 times 4 is minus 12x to the 3rd. So altogether that's minus 24x to the 3rd. And then negative 3 times negative 3 is positive 9x squared. So there's an equivalent form of f of x that we can take the derivative of using the power rule and the sum and difference rule. So then f prime of x is going to be 4 times 16 is 64. X to the 3rd minus 3 times 24 is 72. X squared, and then 9 times 2 is going to be 18 x to the first power. And there's not much else you can do with that. Does anybody have any questions so far? So until we get to something that's called the chain rule, if you had something like this, this is how you handle it. Okay? And we will have a way to handle this that's not exactly the same as this. but you do get the exact same answer. There's more than one way to get derivatives in calculus. Now we want to talk about marginal analysis. Oh wait, I think I skipped over something. When we were on this page, I think we talked about numerical derivatives, but I think it wouldn't hurt to go back and refresh you on how to do numerical derivatives. And it's a little different from the 82 and the 83. Let me get a calculator. So if I want to find the derivative of 6x to the third plus 15x squared, clean piece of paper. Finding y prime at x equals 1. If we did it by hand, then y prime would be 18x squared plus 30x. And at x equals 1, then y prime is 18 times 1 squared plus 30 times 1. So that means y prime is equal to 18 times 1 squared is still 18 plus 30. Make sure I didn't do anything wrong here. So it should be 48. Your calculator gives you this value, because your calculator does not do calculus. It looks like it does, but it doesn't. What your calculator does is it actually takes this function and it gets homed in, like that table that we looked back in chapter 11, it homes in on x equals 1 by coming at it from 0 and by coming at it from 2, until it finally gets two answers that are the same, and for it actually happens at a little tiny bit more than 48. Because there's round off error, because the calculator, as I said, it doesn't do exact arithmetic. All it can do is processes with the last answer that it had. And it can hold 14 decimals inside, so it's actually something else past the 6. But the calculator calculus isn't going to be exactly the right answer like you would arrive at. And that's why I wanted to show you this problem. If you do numerical derivatives, all you need to remember is that you're going to need to round off. Almost without a doubt, you're going to need to round off. And usually my math lab tells you to round off to a certain number of decimal places. And for this one, if it were to tell you round off to an integer, then you obviously round off to 48. Okay? But if we do this using the calculator, there's three different ways to do it. One way you can do it is just simply from the home screen, and the order for this is going to be different. Once again, for the TI-81, the 83 and the TI-84, it's a little bit different. The steps on the 84 are to hit math and go down until you find n deriv. And hit enter. And that's the same for both of us, both the 83 and the 84. I'm going to hit math. I'm going to go down to n deriv. And I'm going to hit enter to select it. Now at this point, the 84 pops over to a screen and asks you to fill in some things. it's gonna ask you, it's gonna give you a little thing. Actually, what the 84 looks like is this. So you'll have to fill in the little X right here. You'll have to fill that in. Then put your function in the parentheses, and then fill in that 1 at the end. So for the TI-84, the things you're going to enter are going to be X, f of X, close the parentheses, don't forget you have to do that because f of X is going to be in parentheses, and then put in the value of X. So there's your step for the 84. The steps for the 83, like I said, are a little bit different. You have to give it first the function. And you can put the function in by actually typing the function. 6x to the third plus 15x squared don't close your parentheses yet. You need a comma, and then X, so those first two steps are reversed. Then you'll need another comma, and then what value of X? Well, that's 1. Okay? And I forgot to close my parentheses, but it did close them for me. Let me go back and make it look the way I should have made it look. Oh, I know why it's the parentheses belong at the end on the 84. Okay, so you're going to put in f of X, and then X, and then the value, and then close the parentheses. But you'll get the same answer both ways. Okay? If you wanted to graph the derivative, and if you remember at the last part of chapter 11, we talked about drawing the graph of the function from the derivative and vice versa. You can actually go to y equals and put in the function, which is 6x to the third, plus 15x squared. Whoops, what did I do? It's supposed to be x.
Is there any way you can move the calculator down a little bit?
Mm-hmm. Yeah, it's up there in the shadow, isn't it?
Appreciate it.
You still see it okay?
Yes, ma'am.
Okay, so plus 15x squared. And then you can use the numerical derivative in y2 and actually show the graph and the derivative. So you just do, again, you do math and deriv. And I could retype that function, but you know what? I really don't want to. I'm just going to go vars over to y vars, choose function, and choose y1, and that way I don't have to type that. And then comma, x, and it'll evaluate the derivative for any number you want. So then when we go to the window, and I'm going to take a clue from the window here rather than hunting around for it, we're going to go to the window and set it up to go from 0 to 3 and from 0 to 250. And since it can't make 250 little tick marks, I'm going to have it put one every 50. And then look at the graph. So there goes my function. That's the function, which is the 6x cubed plus 15x squared. And then this is my derivative, which is 18x squared plus 30x. And what you can see here is the derivative at this point is positive and increasing because this function at this point has a positive slope, and the slope is increasing very quickly. At about this point, it stops increasing, it starts to slow down increasing a little bit. So what's going to happen out here is it's going to be a typical cubic function. The function is going to take on this shape. Okay? And if I zoom out, we might even be able to see that. So we can see here the derivative is the cubic function. So if we trace on it, we can see what's going on. And what we see here is that even though the graph itself can go negative, its slope is always increasing. Its slope is always positive. And at about that point right there, it's still increasing, but it's not increasing as fast as it was.
I have a question. When you do your y1 and your y2, your y2, since we're already calculating that derivative by hand, can we just put the derivative in there ourselves instead of doing in derivative?
Yes.
And it'll
Yes.
work the same?
It'll work. In fact, that's a good way to check to make sure that you did the derivative right, is to put your function in y1, what you got for the derivative in y2, and then what to do the end deriv for what's in y1. Don't even look at y1, you can turn those off. Show you what I'm talking about, because that's a very handy thing to know that you can do. Okay, so we knew that the derivative was 18x squared plus 30x. And at this point, I'm not interested in what the graph looks like. I just want it to be sitting there so I can use it. And if I hit graph right now, I should only see one line. If I type in my answer right, I should only see one line. So there's equation 2 going. And now equation 3, if you watch real carefully on your calculator screen, you can see it's regraphing right over the same thing again. So if I hit trace anywhere on that line, and I go down to y3, it stays the same line all the time. So that's a good way to check whether you did your derivative right or not. Okay? And that's one of the wonderful things about doing a numerical derivative, is that you're able to graph it on your calculator. So it's a good use of technology. Get my stuff in order here. So now we're going to talk about marginal analysis. And for that, I think I want to open up the PowerPoint. Get the calculator out of the way. And you have the PowerPoint, by the way, in D2L. So we're going to talk a little bit about marginal analysis. Marginal analysis is talking about the rate of change in your profit, your demand, your cost, your revenue. Marginal always indicates you're talking about slope or rate of change. So what we're looking at here, if this is a cost function, let's say, where you have a fixed cost of wherever the y-intercept is, and then the function itself is quadratic because it appears to be curved. And what marginal analysis does is it lets you determine the cost of producing the next item. So if you find the marginal cost of the 100th item, then what you've done is you found the rate of change at the 100th item, which tells you how much it's going to cost to produce the 101st item. That's really what it is. So looking at the one we have here, if we drew a tangent at xc of x, c prime of x over 1 would be the derivative. So when I get to x plus 1, let's say this was 1 and this was 2, then this is the change, the marginal change in c of x. The rate of change in c of x, it's the derivative over 1 for one more item. So what you're doing really is a slope process. The tangent line has a slope here, we're moving up to here, so we have an increment of 1. And that's the x plus first item minus the cost of the last item. If we can go to the textbook, I'll show you why that's important. So let's go look at 12.2. On the previous page. Okay, so this, on this page, this is page 648, that's an explanation of what marginal analysis is about. And as I said, it's the cost of producing the next item. So for an example, let's look at how you would work example 6, marginal analysis. And then we'll try to work another example. So it says, suppose the total cost in hundreds of dollars to produce X thousands of a beverage is given by this cost function, C of X equals 4X squared plus 100X plus 500. They want us to find the marginal cost for X equals 5. Okay, that's easy to see that the derivative of the cost function is going to be 4 times 2 is 8X, and plus 100 times 1 is 100, and that X disappears and 500 goes to 0. So this is our slope equation for any value of X. That's our marginal cost equation. And in order to find the marginal cost at 5, we just plug in 5. 8 times 5 is 40, plus 100 is 140. So the interpretation of that is that after 5,000 barrels, because X is measured in thousands of barrels, after the cost to produce 1,000 more barrels is going to be approximately $140, or $100, which is about 14,000. So if we've got to the 5,000 mark, it's going to cost us 14,000 to produce the next 1,000. Okay? It's not that it's difficult to calculate. What's a little harder, I think, is to understand what it's telling you. Now, the actual cost to produce 1,000 more barrels is C of 6 minus C of 5. So the cost for 6 is going to be 4 times 6 squared plus 100 times 6 plus 500, which is going to turn out to be 1244. And the cost of producing 5,000 was 4 times 5 squared plus 100 times 5 plus 500, and that totals up to 11. So it says for the actual cost to produce 1,000 more is $144,100 or $14,400. That's the actual cost. So marginal cost does not give you the actual exact cost, but it gives you a very close approximation. Okay? So after 30,000 barrels have been produced, the cost to produce 1,000 more is going to be given by this equation. So we're looking at X is 30,000. How much is it going to cost us to produce 31,000? So we find the derivative, plug in 30, and it's going to cost us $340,000, which is $34,000. So it cost us, notice that it costs to produce an additional 1,000 barrels is increased by approximately $20,000 when you're at 30,000, whereas it didn't increase by that much when you only made 5,000. Why would that be? Why would this 1,000 barrels only cost $14,400, and yet the 31st 1,000 is going to cost us $34,000? Why would your costs keep increasing? Anybody? If you're producing more and more and more, aren't your costs going to go up? Okay, do they always go up at the same rate? No. Sometimes your costs will decrease at some point. Sometimes they'll actually go down, depending on what happens, because you reach a point where your costs are going to decrease, but it's not ever going to decrease to zero. So you need to think through why these work the way that they do. So that $20,000 in production is a much higher marginal cost. So you probably don't want to produce that many, because for some reason the process is costing more after some certain number of barrels have been produced. So now we're going to try example 7. So you can work with me. So this is example 7. This is an application of marginal analysis. It says the demand function for a certain product is given by P equals 50,000 minus Q over 25,000. And they want us to find the marginal revenue. Now notice they did not give us the revenue equation. What they gave us was the demand function. So what we first do, just flip back to the book a second, because I think that's the one. Yes, that's the one that's coming up next. We'll work from here. The first function is only good for 0 to 50,000. So evidently the demand function changes after they've made 50,000. And find the marginal revenue when Q is 10,000 units. Okay, if you have the demand, how are you going to know what the revenue is when you're demanding something at that certain price? He represents the price. How would you figure out the revenue if you know how many they want and you know how much each one costs? Thinking back to one of the problems on, I think the first test. Let's suppose somebody has a t-shirt shop and she knows what her costs are, she knows what her revenue are, And she knows that the demand is gonna go down as her cost goes up. Okay, because she charges more as her cost goes up. So at some point, she's gonna have to figure out when her revenue is going to be at its maximum point, which is what this is all about, talking about marginal revenue. How does she figure out how much she made at the end of the day? How does she know her revenue from selling, let's say, 100 t-shirts? What would she do with knowing what she charged for the shirts and how many shirts she sold? What tells her revenue? Not quite, close.
Operating cost minus, teacher fund.
Okay, if you're talking just about revenue though, that's the money she's bringing in. Let's say she sells $8, $8 a shirt, she sells 50 shirts. What's her revenue gonna be? No, you're overthinking it. Come on, guys, wake up, you need some caffeine. She's selling 50 shirts and she charged $8 a piece for them. What is her revenue? Revenue is how much money did she take in? $400. Okay. What if she sold 125 shirts at $10 a shirt? $12.50. What are you doing to get the answers that you're giving me?
Just multiplying by
Okay. So if she knows how many, which is what the demand function is, it tells you how many people wanted, and she knows the price that they're willing to pay for them, how would she find her revenue or be able to predict her revenue?
to multiply by how much the demand and price shirts.
Exactly, very good. So that's what we're actually doing here. This is the price at which she can expect that much demand, okay? So this is your demand function, but your revenue function is always going to be your demand times your price per whatever it is you're selling, okay? And Q represents the quantity here. How many will people sell? Somewhere between 0 and 50,000, because 50,000 is all they're gonna make. They're not making any more than that. So this function tells me the demand for how many at a certain price. And if I want the revenue, then I need to multiply the demand by the price. So the revenue function is going to be Q times P, but the price is given by the demand function, because the price is going to change depending on the demand. So you multiply Q times the expression for P. So if you multiply Q times 50,000, you get 50,000 Q. And if you multiply Q times negative Q, you get negative Q squared. And the 25,000 in the denominator doesn't change at all. Okay? And then the only way we have derivative rules to know what the heck we're supposed to do with that is we would try to divide 25,000 into both of those. That's the only place where they kind of skipped a step that I would have put in. Let me just get back over the screen since I've got the problem there. So her revenue is going to be the number she sells times the number of the demand, which is going to be 50,000, minus the quantity over 25,000. And we know that's 50,000 Q minus Q squared, all over that 25,000, but you know what? If I put it under each one separately, I might be able to work this better. So 25 goes into 50 two times, and the thousands all cancel, so that's gonna be 2Q minus, I don't really like the number being in the bottom, I'm gonna change it to a fraction, so that I can treat it more like a coefficient. Okay? So her revenue for Q1000, or their revenue for Q1000, whatever it is that they're making and selling, is given by this equation. And I want to talk about their marginal revenue. So their marginal revenue is R prime. And the derivative of 2Q is what? 2 minus 2 times 1 over 25,000 is 2 over 25,000 times Q. So it's a linear equation. Marginal revenue is linear. It has a constant change. This is going to be kind of hard to work with, so we're going to get a calculator and change that 2 over 25,000 to a decimal. Okay, now that E negative 5, remember, means 0.00008. So that's her marginal revenue equation. And you can see that that's not much change per 1,000 units. And they want to know the marginal revenue from up here when there's 10,000 units and P is in dollars. So the revenue, the marginal revenue, is 2 minus 1,000, which is the value of Q, times 0.00008. And since I've already got that in my calculator, I'll just multiply that times 1,000. Make sure it is, no, it's 10,000, sorry. I wrote it wrong and said it, I wrote it right and said it wrong. So that's 0.8. And 2 minus 0.8 is 1.2. And remember from the top up here, Q is 10,000 units and P is in dollars. So that 1.2 gives us what? Mm-hmm. That's exactly right. It's also 120 per unit, okay? Because marginal revenue, remember, is the difference in the revenue with respect to the difference in the price. So that's $1.20 per 10,000, or per unit, not 10,000, because we use 10,000 in there. So it's per unit, per 1 unit. Pop that back up there. Remember, this is really a slope. It's a rate of change for the next unit. And because we actually use the 10,000 in here, that's $1.20 per unit, not per 10,000 units. Okay? Okay.
Says that their revenue is 16,000.
Excuse me?
Or am I reading wrong?
Where?
Down at the bottom.
Down at the bottom. It says the graphs of the, well, I'll have to show you the graphs of them, but it says the next item sold when she sold 10,000 is each one of them is gonna produce another $1.20. If she sells another 10,000, then what you said was gonna be right, it was gonna be, 12,000, okay? So let me show you the other figures since we don't really want to take the time to graph it. So this is an illustration of that. This is her actual demand function, and it, as you expect, as the price increases, or as the number that are produced increases, eventually demand is going to go to zero. And your revenue equation is 2 minus 2 over 25,000 Q. And notice that it's always decreasing, so your costs are always decreasing. Yes, ma'am?
For some reason, the book and you were getting 1.2, but
Mhm.
I'm getting 1.6.
Let me see what you're doing.
And then it says the revenue with 10,000 is 16,000, not 12,000. So it doesn't make any sense. So right here it says 1.2, but if the revenue at 10,000, how's it going to be 16,000?
Okay, that's the marginal rate, $1.20 per unit.
Oh, it's not. So the marginal is going to be exact when you multiply that by 10,000.
You shouldn't have multiplied that times 2, it's supposed to be 2 minus the other one.
So when you think the marginal, it's not going to be the exact,
It's going to be an estimate.
but it's going to be
Pretty close. Now, if you go back and you graph the original equation that we had, let me pull this back up a second so I can show you why it works the way that it does. If you go back to this, let's see, here's my revenue equation. There's your revenue equation. Notice it's quadratic. It's got a negative coefficient. What do you know about quadratic equations that have a negative coefficient? How do they graph? What kind of shape does a quadratic have? I think I heard somebody say it. It's a U shape. If it's got a negative coefficient, does it open this way or does it open this way?
Down.
It opens down. Well, here's the graph of that revenue equation, so let's talk about it. Revenue starts out when there's none made and none sold, then it's going to be zero. But as they start making them for the first 10,000, then the price is going to go up substantially. And then for the next 10,000, it's still going up substantially. But as it goes from 20,000 to 30,000, what starts to happen to your revenue? Why is the revenue going down?
Demand's not enough.
That's right. The demand is going down because the price is too high. Okay? And eventually, your revenue is going to go to zero because the price got to be too much. Even though the price started dropping after you hit that maximum point. So your maximum revenue is going to be about 25,000. Okay? This is one of the reasons that it's really important to look at the graphs and not just know how to take derivatives. You're going to need to apply this to a real business situation. Okay, and then we're going to look at example 8, and I've got it on the projector. And you've got it in your notes. It says, suppose the cost function in example 7, so don't put that page in example 7 not too far away, because we're still going to need that, one of those functions. It says, suppose the cost function in example 7 is given by C of Q equals 2100 plus 0.25Q. So what that means is if C of Q is in dollars, because that's what the other quantities was in dollars, and Q represents the number in 10,000s. So it's whatever we get for Q times 10,000. And this is only effective as long as Q is less than 30,000. Because remember, 30,000, we're starting to lose money. We're not making anything past 30,000. Okay? Find the marginal profit from the production of the following units. How do you find profit if you've got revenue and cost? Exactly. What does that mean if your profit's negative? You're not doing good. You need to rethink what you're doing. Okay? And it can become negative. So we decided that our revenue equation, put it back up here for a second. Our revenue equation is R of Q, and it is 2 minus, I like this better than I do that. Times Q minus the cost. So I think I'll put cost down here and put it in parentheses. So the cost is 2,100 plus 0.25 Q. So that means that my profit equation, keep wanting to use X, 2 minus 2,100 is what did they do with the 2? Oh, that's supposed to be Q squared. Sorry, I know what they did now. My bad. Your profit equation turns out to be, and that 2,100 is going to be negative at the end of it. Turns out to be 0. I'm sorry, this is supposed to, let me go back and look at that revenue equation. I left out the Q. So it's minus 2,100, 2 minus 0.25 is 1.75. And then this stays the same right in the middle. And they have it as 1 over 2,500, but I'm using it as 0.00008 Q. So here's your profit equation. Let me write it a little neater. So there's profit. Now the only difference in mine and theirs is that I didn't deal with the fraction. I kept this. But this and this are the same thing. So what happens to your profit after you reach 20, 30,000? What's starting to happen? Yeah, it's not gone negative yet, but it's slowing way down. So you need to be looking ahead and thinking, okay, I probably need to hold the price here, if I can. So then it asks you, what is the marginal profit from producing 15,000?
Is one of those Q, the Q squared?
Yes.
I was wondering why you didn't put them together.
This one. It's because I kept forgetting to bring the Q down in the revenue function. Okay, so all you need to do to find your marginal profit at any of these numbers, and we're not going to finish this up, I'm going to let you do the arithmetic part of it, but you're going to have to take the derivative of this. So your marginal profit is going to be 2 times 1.75, which is 3.5 Q, minus 0.00008. That's going to disappear. So Plug that into your marginal profit, and you can answer all three of these, and then check your answer in the book. It's answered in the book. Okay? This pretty much finishes up 12.1. And next week we'll start 12.2. I did adjust some of the homework dates, by the way. And there is, I almost forgot, I think some of you knew it, some of you didn't. There is an assignment in D2L. It is not a calculus assignment. Okay?
Okay, so there's like instructions on.
There's instruction. You're gonna watch 3 videos and write me a couple, 3 paragraphs and tell me what you thought about the 3 videos.
So does it say to go through D2L or send that stuff?
You can send it through D2L. There's a Dropbox in D2L.
Okay.
Okay?
I
Is
can't
that
make
it?
today, I just wanted to make sure I got on the attendance roll.
The quiz was in here, Charles, so I want to make
Okay.
sure you got it. Did you have time to do any of it?
Oh, yeah, I mean, I'm pretty sure I did all the ones I knew how to do. Some of them I just didn't know how to do.
Okay, well, this is not necessarily a grade. It was more attendance taking and then me checking to see where everybody is.
Okay. Are you gonna grade those next week?
Yeah, I'll have them and the ones plus my test grades from last week.
So they just need to be here as well.
Yeah.
Where are those paragraphs from?
First of the week, if not all of Yeah, I know he is, it just. Okay.